In this module, we're going to discuss system privileges, specifically how to secure and exploit them, and how the principle of least privilege plays into security-first design. Our main ideas for this module are going to be what are privileges and permissions, and how are they implemented, how is security-first design supported by the principle of least privilege, and what role do access control and security models play in security-first design, and what are privilege escalation vulnerabilities and how are they introduced when the principle is not followed. First, we need to discuss the general concept of privileges and permissions, the components of operating systems that rely on them for various functions, and privilege configuration, management, and monitoring tools on Windows and Linux. Put quite simply, a privilege is the ability of a user or a service to act on managed computer resources. It can be used interchangeably with the term permission, or in less common cases, the term right. Users, files, and processes are the foundational components of most operating systems, and these generally have standard privileges, including users owning files and launching processes. These processes, in turn, use the files that users own. However, this simple model can quickly get very, very nuanced, and the exact implementation of privilege will vary by operating system, version, distro, configuration, deployment, or a number of other factors. For example, users, while they do own files, they also have privileges to read, modify, or delete files and resources owned by others following the rules of a security model. Administrators on Windows and root on Linux have the greatest privileges on a system, and on Windows, system is an administrator account itself, which is solely used by the operating system and services. On the other hand, standard users on Windows and non-sudoers on Linux have access to their files and processes, and those they are granted access to by others, but no more. Processes generally operate with the privileges of the users that run them, but there are exceptions to this. In Linux, users can run processes as root by using sudo if they are in the sudoers file, and they can run processes as other users by using su or run user, or if the SUID or SGID bit is set on the executable. In the case of su or run user, they would also have to have permissions to run this program as another user. On Windows, users can use the run as drop-down option or command, depending on the way Windows is configured. Services can also be configured to run as a different user or system if the user configuring this has the proper privileges. All of these methods, however, require that seclogon, the secondary logon service, be running. So if this is disabled, none of these features will work. Finally, file ownership and permission usually follows some form of security model or access control for associating users with the permissions they have to edit and modify files. Now that you know a bit about privileges and the components behind them, let's introduce the principle of least privilege. Least privilege includes minimizing the number of privileges granted to a user for accomplishing assigned duties, and disabling privileges that are unused or not required for accomplishing these duties. While they might seem simple, these actions improve accountability and limit the potential for accidental or intentional privilege escalation immensely. The most obvious example of a least privilege implementation is when operating systems prompt users to elevate their privilege for tasks that have high consequences. This would be the Run as Administrator dialog box that you see pop up when you install software on Windows. There are quite a few GUI and command line tools in Windows used for privilege configuration, management, or monitoring. For users, the Local Users and Groups section of Local Group Policy is an easy way to manage different user accounts and their privileges. There's also User Account Control, which you can adjust to prompt users for various actions depending on if their privilege level is allowed to take that action or not. There's also Access Check and Access Enum as part of the sysinternals suite, which can allow you to view various configurations and potentially hunt for misconfigured user accesses on Windows. For processes, there's Process Explorer and Process Monitor, which are also part of sysinternals. These applications can view the processes running in your system, as well as the privileges that they are running on as and where they started from. A relatively new feature in Windows Defender called Memory Integrity can also prevent against process injection. Services, which I'm grouping in with processes here for this case, are also a useful tool to be able to configure in Windows. These can be configured from the Services Management Console, and they can also be configured via the AutoRuns utility in sysinternals, which can find potentially hidden services starting at startup and at other points on your system that are not listed in the Services Management Console. For files, the Advanced Security Settings dialog box under Properties is the typical way to manage file permissions on Windows. There's also the Local Security Audit policy if you have any auditing configurations set up on your box to alert you if somebody is modifying something that they shouldn't be. And finally, controlled folder access in Windows Defender is a relatively new feature. It's generally intended to stop ransomware, but it also takes into account the concept of what the user is doing on the file or folder that they are allowed to do something on, and whether that is a desirable action or not. So in this case, it can block something that a user is allowed to do, but based on the actions the user took on the file might not be desirable. Finally, for the registry editor is the de facto method for editing that. There are other tools, but they are mostly third-party and not as common. I know one additional tool called regshot is especially useful for debugging registry changes, especially for malware analysis, but it isn't solely related to configuration management or monitoring, so I didn't list it here. In contrast to Windows, the privilege configuration, management, and monitoring tools for Linux are usually file or command line based, since Linux treats everything like a file. User configuration is typically done through etc password if you are configuring new users, or etc sudoers if you are configuring users to be able to run as root, or through user mapping on SELinux if you are running Linux in an enterprise environment. You can also set the SUID or SGID bits on applications to allow them to run as specific users, regardless of who executes them. For processes, Linux capabilities are a feature of the Linux kernel that allows for more precise control over the privileges of individual processes. You can also use the process domain in SELinux to configure them, or you can run CVE checker to check to see if there are potential CVEs open on processes that are running and if you need to update them to resolve that. For services, you can use the service utility to start and stop services, as well as check to see what are running and what are not. You can also use cron to determine if there are any timed events that will start services on a Linux system. And for files, you can use chmod to set owners and groups and privileges on files, as well as setfacl, which stands for Set File Access Control List, to configure more granular file permissions on Linux files and folders. You can also use file labeling utility in SELinux, and depending on your configuration, if you set the sticky bit, this will affect certain users' abilities to access specific folders. The privilege concepts we've discussed are implemented in security models. Security models are one way that we can enforce the principle of least privilege, as well as gain some additional benefits. So what's a security model? Security models define rules of behavior for an information system to enforce policies related to system security. These typically involve confidentiality or integrity policies of the system. They define allowable behavior for one or more aspects of system operation, or there's technology that enforces rules of behavior to ensure that the security goals are met. Most operating system implements elements of these security models, but they aren't always perfect implementation of the academic model, since they don't always conform to business needs. So practical implementations are more common, and these are just generally functionally consistent with the goals of these models. When discussing security models, we will use subject-object notation. If you haven't seen it before, it's not too difficult to understand. Simply S and O are subjects and objects, and properties of each are defined with a letter like P. And now we can create associations between subjects, objects, and the properties of both subjects and objects. Bell LaPadula, or Bell LaPadula, both seem to be acceptable pronunciations in industry, so pick the one you favor, was one of the first formally defined security models. It was created to describe essential requirements for the Department of Defense's Multi-Level Security Policy, or MLS. The BLP model assigns a security label to subjects and objects and defines rules for interactions between them. It's really concerned with protecting confidentiality and intended to prevent unauthorized reading. The properties defined in this model are the simple security property, where a subject with this property cannot read or access an object of a higher classification, the star property, where a subject with this property can only save an object at the same or higher classification, and the strong star property, where a subject with this property can only write to objects at the same security classification level as the subject. These can be simply summarized by the phrase no read up, no write down. BIBA is a formal state transition system for cybersecurity policies, and it's really designed to be the inverse of BLP. The BIBA model assigns an integrity level I to subjects and objects and defines rules for interactions between them. It's concerned with integrity and is really intended to prevent unauthorized writing. The properties defined in this model are the simple integrity property, where a subject with this property cannot read or observe an object of lower integrity, and the star property, which means a subject with this property cannot modify an object of higher integrity, and the invocation property, which is a subject with a lower integrity level cannot request access to a higher integrity level object, only to objects at an equal or lower integrity level. These can be simply summarized by the phrase no read down, no write up. The Clark-Wilson model improves the BIBA model by describing its properties at the transaction level instead of at the system level. The CW model assigns a subject program object binding for each transaction and defines rules for two types guaranteeing system integrity. It's mostly concerned with separation of duties and is intended to prevent undesirable changes by authorized subjects. There are 9 rules across 2 types associated with CW. We aren't going to go through them all, but essentially certification rules lay out how the system certifies that a particular data object is in a valid state, according to another set of rules. And the enforcement rules make sure that already certified data objects stay certified or maintain their integrity as the system interacts with them. Access control is another way that we can enforce the principle of least privilege and implement the policies described by the security models. There are several types of access control, which we'll talk about. Access control methods are formal presentations of the security policies enforced by the operating system. They are really useful for proving theoretical limitations of systems, as well as bridging the gap in abstraction between policy and mechanisms through terms called duties. Security models align with access control methods so that they can enforce the policies which support least privilege. There are 2 duty types in most access control implementations: those that are fundamental, which means that on objects, users can read, write, modify, create, delete, and execute, and on security parameters, which would be the same operations except on the security parameters themselves. And the complex duty type, which is a sequence of these fundamental operations to do something more complex, like reading a drive that was inserted or ejecting a drive that was previously read. The first access control method we're going to look at is role-based access control, or RBAC. And in RBAC, the roles assigned to groups of users by systems administrators determine access privileges. RBAC is an access control policy that restricts information system access to only authorized users, so organizations can create specific roles based on job functions and the authorizations or privileges to perform needed operations on organizational information systems, which are associated with the organization-defined roles. In this way, RBAC is essentially an org chart. In rule-based access control, or RUBAC, note the acronym there and how similar it is to RBAC, rule lists define access parameters and apply to all subjects and objects equally. RUBAC is a predefined list of rules to determine access with additional granularity controls, such as when, where, and if the system will allow you to read, write, or execute on special conditions. Rollback is managed by the system owner, and these rules are often expressed in Boolean logic terms, and therefore can be really complex and specific. So therefore, rollback is frequently implemented as ACLs, and you'll quite often see these on routers. In mandatory access control, or MAC, another confusing acronym, don't get this confused with MAC address, access permissions and restrictions are enforced by the operating system based on a security hierarchy. In this model, access control policy decisions are made by a central authority and not by the individual owner of an object, so the user cannot change access rights. This is really common in military and government organizations. They typically use MAC to assign security classification levels to individuals and to data, and therefore to map the associations between them. Discretionary access control is probably one of the more complex access control methods we'll look at, because the data owner has full control over objects they create, and they assign specific privileges through other users that way. Basically, DAC leaves a certain amount of access control to the discretion of the object's owner, or anyone else who is really authorized to control that object's access. The owner can determine who should have access rights to an object and what those rights should then be. DAC really allows for the greatest flexibility of control, but it's also the most vulnerable form of access control due to the reliance on the user. The object's owner can pass on control weaknesses that can contribute to access and privilege aggregation and just have a compilation or compounding there of potential access and scope creep. Many commercial operating systems used on endpoint devices such as Windows and Android will use forms of DAC so that purchasers, the individual or an organization, can choose how to tailor these controls to their own needs, but more often than not it's replaced, if possible, with a more centrally managed form of access control. Obviously, in DAC, users set their own access rules, which would be the key thing to remember about this access control method. In attribute-based access control, or ABAC, the attributes assigned to groups of users by systems administrators determine access privileges. ABAC is an access control method where access rights are granted to users with policies that combine attributes together. And the policies can use any type of attributes, like user attributes, or resource attributes, or environment attributes, etc. Essentially, in this way, it's a simpler form of rollback, but it applies multiple attributes instead of a single role to the user. It can be more flexible in this way as well. Now that we've covered privilege, security models, and access control, what happens when something is misconfigured on a system? Typically, this exposes it to what's known as a privilege escalation vulnerability. Privilege escalation, or PrivEsc for short, is the act of exploiting configuration errors to gain unauthorized access into a system. It's typically one of the middle steps of the cyber kill chain, so after the initial access to the network is obtained, but before the adversary acts on their final objectives. It's a stepping stone to get to more sensitive data or more permissive accounts, essentially. There are two techniques for privilege escalation: horizontal, which is user to user, and vertical, which is user to administrator. Horizontal privilege escalation involves accessing another user's account and abusing the legitimate privileges granted to them. It's also called lateral movement or account takeover, and the reason attackers really like this attack vector is because it can be easier to obtain access to protected enclaves than going through an administrator or root account first, essentially going directly to an interesting target rather than going up to root or administrator and then going back down to that user or target. If they can just get there directly, they would probably prefer that. The reason they find these users interesting is because these protected enclaves usually have data that isn't accessible to the rest of the organization, like payroll and HR, which often have access to specific systems containing employee PII, which might be good for stealing identities or running scams. Engineering staff may have access to proprietary company information, including trade secrets, which might be interesting to competitors or a certain nation state, as well as the construction, maintenance, and janitorial staff, which may have access to building design blueprints for any adversary looking to infiltrate a facility physically. Vertical privesk involves increasing privileges by obtaining access to administrative on Windows or root on Linux users or service accounts. Attackers typically use this initial access accounts to search for other accounts with these higher privileges or accounts through which they can pivot to get them. And if the attacker can get this level of access, they essentially own the system. They can control or add services that start with privileges of the system itself, which could be very difficult to detect or remove. As you can see in the diagram, the pivoting could potentially involve going from a standard user that they've infiltrated up to the privileges of the IT help desk rep, and then if they are an administrator themselves, to becoming the Windows NT authority, or what is now called the system account. There are quite a few configuration errors in Windows that can be abused to obtain privilege escalation. I've collected some here, but this is by no means a comprehensive list. There are many, many, many ways Windows privilege escalation vulnerabilities can be exploited, and you can search for a lot more than I've included here, but I believe these are some of the most common ones. To start, privileged services should not be editable by standard users, but this is the default, but if standard users are able to edit privileged services, they can potentially direct system starting services to any binary. Along the same lines, the registry should not be editable by standard users because they can do much the same thing, as well as many other undesirable actions. Passwords shouldn't be stored in text files. If the password is stored for a privileged account is stored in a text file in an unprivileged account, it's a very simple privilege escalation vulnerability because anyone can log into that privileged account then. Not properly protecting the security account manager or requiring the appropriate privileges to query it. This could result in somebody taking Mimikatz and dumping the hashes from the security account manager and potentially gaining a privilege escalation that way. Service executables should not be modifiable by standard users. If they can modify the executable at the path that a service is executing, they can replace it with pretty much any other binary. Uncoded service paths are a similar concept, except they have to do with the way that the service manager parses these paths. In general, any paths for services on Windows need to have quotes around the entire path, or the service manager will interpret any paths with spaces as a command with arguments. So it will go down the string, and as soon as it finds a space, it will try to execute the binary before the space with the arguments after the space. If that binary doesn't exist, it will continue parsing until it finds the next space for the end of the string and repeat the process. Typically, the binary that you desire is at the end of the string. So if any other user has access to any part of the path prior to that ending binary, they can insert a properly named executable there, and the system will execute it as if it is the service it intends. Insecure local administrator accounts. Local administrator accounts can, depending on the configuration, be used to gain domain administrator account credentials. So it's very important to only use local administrator accounts for things that are needed and to secure them properly or disable them when they are not in use. Finally, third-party apps that launch system-level processes or shells. This isn't as common anymore, but if there is an application that must run as administrator to function, and anyone can start that application and it drops a shell, they can drop to an administrator shell through that. There are also quite a few configuration errors in Linux that can be abused to obtain privesk. Once again, this is not a complete list. These are just some of the most common ones. If you want to know more about other PrivEsk vulnerabilities, you can simply search for them, and there will be a tremendous amount available for you to explore there. But let's look at some of these. System-wide cron jobs with editable paths. If you have a cron job that is running as root, and someone can edit the path that that cron job executes, someone can start essentially any program at a certain time on a Linux system. And the only inconvenience to this for an attacker would be that they would have to wait until the time that that cron job starts, which could potentially be a while away, but they could obtain a root shell this way in a certain amount of time. Programs with significant capabilities can be security issues. We discussed capabilities earlier in this lecture. Improper use of SUID, SGID, or sticky bit, as we also discussed earlier in this lecture. Make sure if you are setting these bits on programs that you know what the program does and why you need it to run as a different user. If you SUID or SGID something to run as root and that program can drop a user to a shell, that will drop them to a root shell. Allowing SSH as root is obviously an issue because somebody could find your SSH port open and try to brute force the root password, and if they can do that, they suddenly have root access on your box. Folders with write permissions in your path. Your path is essentially a way to enter a shorter command which will expand to a longer command and then execute the binary at that location that the longer command is pointing to. Since most people don't actively look at what the shorter command expands out to, if somebody can replace that binary in the end with a reverse shell or something similar, they can get root on your box when you run the command. In insecure sudoers configuration, it's obviously an issue. Make sure that if you are going to grant someone sudo access, the ability to run as the root user on your box, that you understand why you're doing this and that you remove that access when they do not need it anymore. Passwords stored in text files is the same as on Windows. If you store a password for a more privileged account in a less privileged account, someone who gets access to that less privileged account will have access to that more privileged account. Finally, PAM misconfiguration. This is a unique one to Linux and to Linux distros that use PAM. Essentially, you can configure PAM or misconfigure PAM to not require password authentication to log into a box. And if you are going to modify PAM, you should ensure that you know what you're doing so you do not accidentally misconfigure it so that anyone can log in with any password and it will be considered valid. This concludes the lecture for this module, so let's review. We know that a privilege is the ability of a user or service to act on managed computer resources. We also know how privileges are implemented and how they affect access to files and resources. We know that the principle of least privilege supports security first design principles, and we know how access control methods and security models play into this principle. Finally, we discussed horizontal and vertical privilege escalation, or PrivEsk vulnerabilities, and some common methods to escalate privileges on Windows and Linux due to configuration errors. In the lab for this module, you'll investigate, exploit, and correct many common vulnerabilities that may result from not adhering to the security first principle of least privilege. This lab will span both the Windows and Linux privilege escalation techniques that we covered in lecture. I've shared the CSC840 Security First VApp with you in DSU's IA lab. You should clone the VApp to your account before you start it or make any changes so that you have a clean snapshot to revert to in the event that something goes wrong and you are not able to boot the box or not able to go back to the work that you were working on. So the table in the center includes the box name and the lab credentials that you'll need. You are free to install whatever tools you would like to complete the assignment. I've installed a couple potentially helpful tools on the Linux exercise VM if you would like to use them, but as always, you are not required to. That said, good luck and do let me know if you have any questions.